Power of the dark side.
The James Webb Space Telescope is an infrared detecting observatory which will orbit in the second Sun-Earth Lagrange point, far beyond Earth's moon. It has a large sun shield which separates the observatory into a warm, sun-facing side and a cold, anti-sun side. Webb will observe primarily the infrared light from faint and very distant objects, but all objects, including telescopes, also emit infrared light in the form of heat energy. To avoid swamping the very faint astronomical signals with radiation from the telescope and its instruments must be very cold. We recently learned that you can use polarizers to determine what, if any, light passes through a filter whose long molecules are aligned with each other. Light that is polarized in the same directions is able to drive electrons along the length of the molecule and lose energy, while light that is polarized perpendicular loses much less energy in the filter. If you place a second polarizer after the first one, its orientation determines whether all or some of the polarized light is seen after the polarizer. The sun shield for the Webb telescope incorporates the same idea, by filtering heat. It has 5 layers, each which is cooler than the one below. The heat is radiated out from between the layers, and the vacuum between them is a very good insulator. Because of the time it takes light to travel, the further away an object is, the further back in time we are looking. The Big Bang caused the universe to expand, so most galaxies are moving away from each other. The most distant and youngest are moving away so quickly that the light they emit is shifted towards the red end of the spectrum. The Herschel Space Observatory is an infrared telescope built by the European Space Agency, currently located in the same orbit that Webb will be. The primary difference between Webb and Herschel is wavelength range. Webb goes from 0.6 to 28.5 microns, whereas Herschel goes from 60 to 500. The Webb telescope will look back through time to when galaxies were young. It will observe galaxies that are over 13 billion light-years away from us. Webb needs a large mirror to see these faint objects, and since a telescope's sensitivity is directly related to the size of the mirror area that collects light, Webb's primary mirror will be 6.5 meters in diameter, 7 times the collecting area of the Hubble telescope. Webb's primary mirror consists of 18 lightweight but rigid segments made of beryllium, but coated with a fine layer of 24-karat gold. The beryllium is capable of handling extreme cold, and the gold reflects red light extremely well, making the mirror 98% reflective, whereas ordinary mirrors are 85% reflective. The James Webb Space Telescope has an ambitious design that tackles the 2 main challenges for an infrared telescope: a large mirror to capture long infrared wavelength and a cold environment to deflect unwanted sources of infrared. According to a group of international space experts, including David Sabral, 95% of all stars that will ever form have already formed. Although this is not a definitive fact, it makes the information that present stars hold even more important. Ultimately, the James Webb Space Telescope will bring us the clearest picture ever of baby galaxies, just forming stars, clouds of gas and dust, and more. This will uncover vital information pertaining to our cosmic origins and maybe even shine light on the possibility that we are not alone in the universe.